Good day, everyone. I am Michael Jeff Biompo. So we're gonna tackle about the pigeonhole sort algorithm. For the overview is pigeonhole sort algorithm, time complexity, test case, algorithm assessments, and algorithm discussions. For the abstract is the pigeonhole sort algorithm is a distribution sorting technique particular, particularly well suited for datasets where the range of input values is relatively small compared to the number of elements. This algorithm operates by mapping each element of, of the input array into a series of pigeonholes or buckets, which correspond to specific value ranges. Pigeonhole sort Pigeonhole sort is a non-comparative sorting algorithm that is effective for sorting lists of integers, where the number of possible key values is close to the number of elements. It is particularly effective when dealing with small ranges of integers and lists with approximately the same number of elements and key values. So, as in pigeonhole sort is in the word non-comparative sorting algorithm. So unlike in traditional comparative sorting like quicksort, bubble bubble sort, and merge sort, pigeonhole sort doesn't compare elements against each other to determine their order. So it just relies on the value of each element directly placed in. So pigeonhole is particularly effective when dealing with small ranges, integers, and lists with approximately the same number of elements. So pigeonhole sort is particularly effective when the number of possible keys or the range is close to the number elements. And in pigeonhole sort is originally described by A. J. Lotka in 1926. It was independently rediscovered by John Nant in the 1960s. So pigeonhole sort uses the concept of pigeonholes to distribute elements and collect them back in a sorted order. So pigeonhole sort works. So number one is determine range, two create pigeonholes, three distribute elements, and four is collect elements. So in number one, determine range is find the minimum and maximum value in the list to determine the range. So in two is create pigeonholes, create an array of pigeonholes or buckets to hold the elements. The size of array is the range of the elements. So in three is distribute elements, place each into its corresponding pigeonhole based on its value. So in four is collect elements that traverse the pigeonholes and collect the elements back into the original list in sorted order. So for this slide is we see the advantages and disadvantages. So for the advantages is simple and so pigeonhole sort is just simple and intuitive and efficient with the range of key values is small compared to the number of elements. So pigeonhole sort disadvantages is not suitable for large ranges of key values. Space inefficient for large ranges as it requires additional memory for pigeonholes. And for the last is the pigeonhole sort is best used in scenarios where the range of input is known and limited, making it a specialized sorting technique with a practical application in certain contexts.
Good day, sir. My name is Irish Australian. I will be discussing the pigeonhole time complexity. Pigeonhole sort is a simple sorting algorithm that's particularly efficient for situations where the range of values in the input array is relatively small compared to the number of elements. Its time complexity is often expressed as O(n) plus range, where the n represents the number of elements in the array, and the range denotes the difference between the maximum and minimum values in the array. So, the pigeonhole sort, it is a simple sorting algorithm that's particularly efficient, especially for those situations where the range or the maximum and minimum values were relatively small compared sa number of elements or number of values inside the array. As for its time complexity, it is often expressed as O(n) plus range, where the n kay ga-represent siya sa number of elements in the array. So, mo ang values sa sulod sa array. Number of values. And then, sa range, kay mo na siya ang ga-denote the difference between the sa maximum and minimum value sa sulod sa array. So, next kay as for the discussion, I will discuss the mura siyang steps, but then mas masabtan ninyo siya later on sa next reporter. So, first is finding the minimum and maximum value. So, una, pangitaon sa ang pinakagamay, pinakadako nga value sa sunod sa array. So, need yun niya agian ang tibuok array at least once para mas makita gyud kung asa ang maximum o minimum value. Kay puntahay daghan kaayo, so kailangan jud tan-awon jud ninyo sa ganidon ninyo siya og tan-aw. So, ang kani nga process kay ga-consume siya og O(n) time. Next kay the calculating the range. So, once nga nakita na pag nakita na nato ang minimum ug maximum value, kay dali na lang siya it can be computed in time. Kay kanang since it involves simple arithmetic operations, so dali na lang siya ma-compute. So, third kay creating an array of vectors. So, kani siya kay ang pigeonhole sort man gud kay nagagamit siya og auxiliary data structure or array of vectors para pansamantalang imbakan sa mga elements samtang ginabuhat pa ang process sa pag-calculate. So, ang size aning auxiliary array kay gabi siya sa range sa input array. So, sa pagbuhat pa lang ani nga array daan, kay apil lang ang paglaan ng memory for each vector. So, kani siya nga process kay kanang pwede siya ituring nga isa sa operation as constant time. Kay ma-consume gyapon siya time during process. So, next kay assigning elements to respective holes. So, having an auxiliary array, ang algorithm kay galup gihapon na siya sa input array. Gina-compare ang each element kung asa ang mas dako ug asa ang mas gamay, and then i-compute. Once nga ma-compute na ang total value ato kay gina-assign na sa iyang respective holes. So, diri sa arranging next kay lastly arranging elements into the output array. So, diri ganiro na siya kanang ma-arrange na siya. So, pag ang tanang element gani kay naplastar na, ang algorithm kay gapadayon gyapon siya og check. Kailangan gyapon ni agian tanang elements kay basig kanang wala nakita nga value. And then ang bilang of each elements kay ga base ni siya sa range of values. So, kani nga process kay ga-consume siya og time complexity na O range. Next. In summary, the overall time complexity of pigeonhole sort can be expressed as O(n) plus range. While it may seem less efficient when the range is significantly larger than the number of elements in the array, it shines when sorting integer arrays with a relatively small range, providing a straightforward and effective solution for such
I
scenarios.
am Mark Negara and I will be discussing the real-world simulation. So, the pigeonhole sort is an effective sorting algorithm that is especially helpful in certain situations, like arranging books in a library with few categories. So, the real-world problem or the scenario that we've come up is the book arrangement per genre. So, we believe that the pigeonhole sort algorithm is best, or let's say most efficient in sorting the books per genre. So, in a hectic world of bookstore inventory control, effective book organization is essential to maximizing revenue and ensuring customer satisfaction. Books are categorized into genres based on the quantity of stock received using the pigeonhole sort algorithm. This is a reflection of what occurs in physical bookstores where inventory needs to be constantly changed to serve customers properly while occupying the least amount of shelf space possible. So, the test cases are designed to assess how well the pigeonhole sort algorithm performs in managing inventory in bookstores across the range of real-world scenarios. So, I've created two two scenarios that will be facing in the bookstore, but it will also show how well the pigeonhole sort algorithm can solve the problem or the issue, and I will discuss about it later and show you the simulation about it. So the dynamic process of managing bookstore inventory includes addressing a range of situations from regular deliveries to unforeseen demand swings. We can evaluate the pigeonhole sort algorithm's efficacy in solving issues that bookstore managers and owners encounter in real world by putting it to the test in various scenarios. So this is the scenario that I've created or come up with. So in the test case or the case 1, we have the daily shipment of books. So this test case is designed to evaluate the algorithm's ability to organize genres under typical delivery conditions. So watch the simulation that I will be playing here. So as you can see, the test case 1, the daily shipment of books, it shows us that the pigeonhole sort algorithm is very efficient in sorting the books per genre. Now how about the test case 2, the unexpected surge in mystery genre? So as you can see, in the first simulation, there are 5 different genres. Okay, so and one of the genre is the mystery genre, and The test case 2 says that it will be the mystery general have a spike, or let's say a sudden surge or increase in the shipment. So how will the pigeonhole sort algorithm handle the problem? So in this scenario, evaluates how well the algorithm can adapt to abrupt changes in inventory levels.
Performance evaluation of pigeonhole sort. We all know naman is pigeonhole sort measure how long it takes to sort for classes of different sizes like small, medium, and large classes. 1. Measure average sorting time for various array size and ranges. So suppose we measure the average sorting time of pigeon sort for arrays of different sizes. So I have an example here. So this is our array integers 427316. So the small array is 427. The medium array is 53164. The large array is 10, 8, 15, 12, 9, 6, 14, 11, 7, 13. By comparing the sorting times, we can demonstrate how pigeonhole sort performs across various array size. 2. Assess memory utilization. Assess the memory utilization of pigeon sort for arrays with different value ranges. Like for the example, the array of integers range. So this is array range for 1 to 10. So this is the array range of 4275316, and this is the array range of 1 to 100. Analyzing the memory usage will provide insight into how pigeon sort manage memory allocation for varying values ranges. Number 3. Benchmark against counting sort and radix sort. Compare the performance of pigeonhole sort with counting sort and radix sort using a common datasets to highlight the strengths and weaknesses of each algorithm in terms of sorting efficiency and memory utilization under similar conditions. So that's a benchmark against counting sort and radix sorts. Evaluation methods. Consider these two arrays with different numbers of elements. Computational resources analysis, CPU, time, and memory usage. Measure the CPU time taken by pigeonhole sort to sort both arrays to evaluate the algorithm's computational efficiency handling arrays of varying size. Scalability testing. Performance with increasing array size and case ranges. Test the scalability of pigeon sort by sorting arrays of increasing sizes, like 100 elements, 1000 elements, to observe how the algorithm performance changes with larger datasets. So on this parts this is the example of pigeonhole sort, like time complexity, O(n) plus n, space complexity, counting sort, time complexity, O(n) plus k, similar implementation, different memory usage. Different implement counting sort an array with values between 0 and 5 to demonstrate its time complexity based on the number of elements in k range. So, radix sort, time complexity OD n plus k. So, the sort or list of integer using radix sort to showcase the complexity with respect to the number of digits value range in the datasets.
Algorithm discussion of pigeonhole sort. Um, Algorithmic strengths of pigeonhole sort. So, pigeonhole sort offers several notable advantages, especially in specific scenarios where it outperforms traditional comparison-based sorting algorithms. So, here are the 4 key strengths of pigeonhole sort. First is efficiency for small and well-defined ranges. So, like linear time complexity. So, pigeonhole sorts operates with a time complexity of O n plus m, where n is the number of items to be sorted and m is the range of possible key values. And this makes it exceptionally efficient when the range of the input data is small compared to the other number of items. In such cases, pigeonhole sort can significantly outperforms algorithm like quicksort and merge sort, which have a time complexity. So, say for example, consider sorting the ages of 100 students in a school where ages range from 5 to 18 years old. So, with pigeonhole sort, we can create pigeonholes for each age from 5 to 18 years old and quickly sort the students in time. So, number 2 is simplicity and conceptual clarity. So, pigeonholes as categories. So, the algorithm uses the concept of pigeonholes to categorize elements based on their key values. This straightforward approach simplifies the sorting process, making it easier to understand and implement. Number 3 is stability. Maintaining order of equal keys. Pigeonhole sort is a stable sorting algorithm, and this means it preserves the relative order of elements with equal keys. Stability is particularly important in applications where maintaining the initial order of identical elements is necessary, such as when sorting records by a primary and secondary key. And lastly is memory efficiency. So, in place operation, the algorithm pigeonhole sort functions in place, meaning it requires no additional memory beyond the array used for pigeonholes. This is advantageous in memory constrained environments where conserving memory usage is critical. So, for practical applications, pigeonhole sort is especially beneficial in scenarios where the input of data range is known and small, such as sorting small sets of integers, like when dealing with a limited range of integer values, and like sorting data with fixed ranges, and data with secondary sorting criteria, where stability is essential and the primary sorting criterion has a small range. No, so pigeonhole sort's strengths lie in its linear time complexity for small ranges. stability, and more efficiency, making it a powerful tool in the right context. Next is limitations and challenges of pigeonhole sort. Well, pigeonhole sort has notable strengths. It also comes with several limitations and challenges that can affect its applicability in certain scenarios. First is space complexity. High space requirement for large ranges. The algorithm pigeonhole sort has a space complexity where n is the number of items and m is the range of possible keys values. So this can be problematic when the range is significantly larger than the number of items. In such cases, the memory required to create the pigeonholes can be excessive and inefficient, leading to wasteful memory utilization. So number 2 is unsuitability for broad and unlimited ranges. So like memory constraints. For datasets with a larger or unlimited range of key values, the number of pigeonholes needed can become impractically large. This is not only increases memory usage but also negate the benefits of algorithms' linear time complexity, making it impractical for such use cases. And lastly is the data format constraints. Under of data format constraints is limited to easily mappable data. So pigeonhole sort is designed to work with data that can be directly mapped into integer keys. This restricts its applicability to scenarios involving sorting integers or discrete numbers. It is also not suitable for sorting data types that cannot be easily mapped to a finite range of integers without additional pre-processing. And lastly is comparative analysis of pigeonhole sort. So in a comparative analysis, pigeonhole sort demonstrates its strengths in specific contexts, particularly when dealing with datasets that have a small and well-defined range. So here's a breakdown of how it compares with other popular sorting algorithms. Optimal context for pigeonhole sort. First is linear time complexity. So pigeonhole sort excels with the time complexity, making it highly efficient for datasets. And this characteristics is particularly beneficial for tasks such as sorting students' grades and where the range is limited and predefined. So second is simplicity and efficiency. The algorithm's straightforward approach make it easy to implement and understand, providing clear advantages over more complex sorting methods for suitable datasets. So, for example, sorting student grades which range from 0 to 100, pigeonhole sort efficiently places each grade into its respective pigeonhole, resulting in a quick sorting. So number 2 is comparison with other linear time algorithms. So first is counting sort. Counting sort is similar to pigeonhole sort. Counting sort works well for datasets with a known and limited range. However, counting sort can be more space efficient when the range is not excessively large. Second is radix sort. Radix sort extends the principles of pigeonhole sort to handle larger ranges by processing digits of characters separately. This makes it's suitable for sorting large numbers of strings, offering a method to efficiently manage more complex datasets. So in summary, pigeonhole sort is an excellent choice for sorting datasets with a small and well-defined range of integer keys, providing simplicity, performance, and reliability. However, for more diverse datasets or larger ranges, other sorting algorithms such as quicksort, merge sort, and counting sort may be more appropriate. So understanding the strengths and limitations of pigeonhole sort allows for informed decision making when selecting the most suitable sorting algorithm for a given task. And that's all. Thank you.
Holy Grail.